So today we're going to learn how to translate graphs, and so hopefully stapled to your lesson or on the back of the lesson you should have a group of graphs, and those are called parent graphs. And what we're going to do today is we're going to learn how to move those and how those affect the equation. So the first thing I want to show you is this right here. So if you notice in here I have a square root graph. It's right there. I also have a quadratic, and I'm going to show an absolute value. And if you look here on the left-hand side, you can see all the functions right there. So the square root one is over there, g of x, h of x is the squared one, and I of x is the absolute value. And so what I'm going to do is I'm going to slide these things. So the first thing I'm going to change is I'm going to change the b, and so that is the number that is on the outside. So if you notice as I increase b, it becomes smaller and smaller. So that is the number on the outside, on the inside of the function. If you look at the functions over there, see how they're getting bigger and bigger. Okay? And then as I make it smaller, it stretches out. Okay? And so that's how the number on the inside, whatever's multiplied on the inside, changes it. Now I'm going to change the number on the outside. So notice the same kind of thing happens. The number in the front of each of the functions, it makes it skinnier and skinnier. It's hard to tell the difference between the a and the b, and I'll talk about that more when we go back to the lesson. The big thing is what I'm going to change now is the number on the inside of the function that's being subtracted. So if you notice the graphs, all three graphs are moving to the right. And so if I move it to right there on the 2, if you look at the equations on the left, each of those equations have a -2 either underneath the square root or inside the parentheses with the squared on the outside or in between the two lines of the absolute value. So whenever you subtract something on the inside of a function, it moves the graph to the right. And if I would move in the opposite direction, move it to the left. Now I'm going to move this last one. Notice all of them are moving up. So if I stop it there at 2, if you notice on the equations on the left, there's a +2 after the square root symbol, after the squared, after the absolute value symbols. That adding 2 on the end moves it up 2, and you can also, if you subtract, it would move it down. So now let's go back to our lesson. So we just talked about how whenever you add something on the end of a function, it moves the function up. So if I have a plus any number that can go in there for that k, f of x moves up whatever k is. And so this last box, I'm just going to do an example. So say our parent graph is going to be the square root of x. And so if we want the square root of x graph, the square root graph, to move up 4, you just put a +4 outside of the absolute value. Same with all the other parent graphs. If it's outside of the square root. If it's an absolute value, you put it outside the absolute value. If it's a square or quadratic, you put it outside of the square. And so then if it's subtracted, f of x moves down. And so that would be the same thing as if I did square root of x, that would move it down 4 if I put a -4 on the outside. Now if you have subtraction on the inside, f of x moves to the right, whatever that number is. So if I wanted this square root graph to move to the right 4, what I'd do is I'd include that 4 underneath the square root symbol. And same if I was talking about a quadratic, I would include it inside of the squaring process. So like another example, if I'm using a quadratic, I would put the -4 inside of the parentheses. Now if I want it to move left, I put a plus sign inside. So if I want this example to move left, I do +4 underneath the radical. All right, then we talked about how if I showed you if there's a number on the outside, what that does is it vertically stretches it. And so that was a little bit hard to see that this is a vertical stretch, and if it's multiplied on the inside, so if there's a number multiplied on the inside, it's a horizontal stretch. So we're not going to be doing a whole lot of these. But here's what an example of the equation would look like. So if I wanted to vertically stretch it, I put the 4 on the outside. If I wanted to horizontally stretch it, I'd put the 4 on the inside. If you have a negative on the outside of your function, what happens is it flips upside down. So if I want to flip the square root graph upside down, I put a negative on the outside. And then if I put a negative on the inside, what it does is has a vertical reflection, so it just flips the other way. And so that would look like if I had square root and the negative was on the inside. So now we're going to practice some things. So it says, what is the equation for the following graphs using the parent function? So if you're looking at the paper that is stapled or on the back of your lesson, you should be able to identify that this graph right here, for example, 1, is an absolute value graph. And so the parent equation for this is absolute value of x. But this has been moved around. So I always just like to look at the original point. The intersection on the original one is right here. So here's the original one. And so I moved my point moved from here all the way up to here. And so how that moves is it moved to the left 2 and moved up 4. Okay, so how you would reflect that in your equation, I would take my parent graph, and if I'm moving left and right, it's going to go inside of the absolute value symbol, and if I move up, it's going to go on the outside. So left is plus, so to go left 2, I do plus 2 on the inside, and up is plus as well, so up 4. So if you would graph that in your calculator, then you would get that graph exactly that's on your paper. All right, example 2, you have to look at your parent graphs and identify this as a cubic, and so the parent equation is x cubed. And so the original graph looked something like this. And so I just, again, compare. It was crossing here, and now it is crossing up here. So what happened to this one is it didn't move left or right at all. It moved up 54 because of the ordered pair that's given to us, and it also flipped. So if I want to flip it, I have to put a negative on the outside, and it went up 54, so I just put a plus 54 on the outside. If I wanted to move left and right, let me just show you off to the side what that would be. So say this moved left 3. Then what you do is you put plus 3, and then you put the cube on the outside of the parentheses. Okay. All right, the last one, the parent for this one is a square root, so square root of x. And so the original graph looks something like this. And so the center of it moved, and it moved left 2 and up 1. It looks like it stretches a little bit, but since we can't really determine, we're going to kind of just ignore that for now. And so if I want to move left 2, it's got to be underneath the radical, and the up would have to be outside the radical. So left, again, is plus. So plus 2 is underneath the radical, and up 1 is plus 1. And that's my equation. And again, if you graphed it. So now I'm given a unique parent function f of x. So there's this strange function that is not listed on your parent function list. And so you're going to sketch a graph of a given transformation. And there will be one of these on your test. So example 4 says f of x plus 4. So you first need to identify what is it asking me to do. So since there's a plus 4 on the outside, it's asking me to move this graph up 4. So how you want to do that, so I'm going to do this one in red, is I'm going to just pick a few key points in this, like here. And I'm going to move each of those points just up 4. So move that up 4, move that up 4, I'm going to move that up 4, and this one up 4. And then I'm just going to reconnect these in a manner that it looks like my original graph. All right, now the second one, this one is asking me to move it to the right 3 and down 1. So I'm going to take each of those original points. I'm going to move it right 3, 1, 2, 3, and down 1. So right 1, 2, 3, down 1. And this one will go off the graph a bit. It'll be right here. Okay. So then I connect it again in a way that it looks like my original function. All right, and then the last one right here, that has been vertically reflected. So how you want to do that is it's basically being reflected over the y-axis. So whatever point I have, so if I'm looking at this point, if it is 4 away from the y-axis, I'm going to plot it 4 away on the other side. Same with this one. That is 2 away, so I'm going to plot it 2 away. This one is 1 away on the right, so I plot it 1 away on the left. This one's 10 away on the right, so I'm going to plot it 10 away on the left. And then I'm going to play connect the dots, just like this. So it doesn't have to be perfect, and the one on the test is a little bit easier. All right, for the last thing, let's draw the following functions without a calculator. So you first need to figure out what the shape would be. So in this case, I noticed the absolute value symbol, so I know the shape's going to be a V. Then I figure out what's happened to this. Well, if it's plus 5 on the inside, that means it moves to the left 5 and down 3 because it's minus 3. So I'm basically going to take that V that originally resides right there, and I'm going to replot it so that it's left 5 and down 3. So that would be the new center right there. And I'm just going to make myself a V right there in that center. It doesn't have to be perfect. All right, the last one, that little square right there, indicates to me that it's going to be quadratic, so a U. And this has a couple things. What it means, because it has that negative sign, it's going to be flipped. Because of the minus sign on the inside, it means it's going to be to the right 4. And the plus 1 means it's going to be up 1. So originally, it looks like this. And when I replot it, I'm going to replot it right 4 and up 1. So the center will now be right there. But it's going to be flipped. So when I draw my U, I'm just going to flip it over itself.